Alright, let's get going. So basically this lesson is continuation from the previous one and the one before. I think even the one before that one. Okay, so it's all about grouping, aggregation, and yeah, it's just basically about grouping and aggregation, quite frankly. We're also going to touch up on how we can create a TSQL queries that do many different things at the same time. Well, at the same time, procedurally. So we can declare a temp table, then put some values in it, insert some data, update it, and then do some select out of that as well. So who can remember what we've done last time? Huh? CTE. Good. Big difference. Okay, CTE. Basically, we were looking at how the execution plans work with subqueries, and also introduce you to CTE, which is, don't remember what it stands for. Does anybody remember what it stands for? CTE. Current transformation ethos? No? No, it's not. No, I can't remember. Anyway, what it stands for. But what we're going to be looking today is grouping, primarily grouping, and different types of aggregates. Do you know what aggregates are? Aggregation is. Anybody? Please speak to me. I'm trying to make it more interactive. Come on. Say something. It's basically summing things up, yeah. Aggregation. So you've got like 1, 2, 3, 4, 5. But 1 plus 2 plus 3 plus 4 plus 5. That's an aggregate. And then count of that aggregate would be 5 numbers. Average would be 1 plus 2 plus 3 plus 4 plus 5 divided by 5. Well done. You just about graduate from a primary school with that knowledge. Alright, so that's basically aggregation. Obviously we have rows or tuples out of our views. What we can ask SQL Server to do is to aggregate those numbers. For example, if we've got a product ID or product name, and we've got like a value like product number like jam, for example, or order quantity 1, then pizza order quantity 2. You can say, and then jam for another order, another quantity 1. You can say, okay, group by jam, which is the product name, and then sum up all the order quantities for jam, and we'll say, okay, jam on the first row plus 1, pizza on the other row plus 2, then another jam plus the previous plus 1, etc. So you get 2 jams and 2 pizzas. Just about right. Consistency. All right. So let's get ahead with this. And what I want to do is basically do some working with AdventureWorks, analyze some sales data, and then I'm going to start adding things like include inventory into the sales data, and then some other information, more complex information out of the database. Okay, so the first query that I want to run, the sales order details, and just look into that table individually just to see what sort of stuff it actually contains. There's no such table because there's a schema for it. Okay? We'll go through schemas in 3 or 4 weeks time. It's actually quite good for those people even who know SQL Server more or less, because we now all our ADM systems and everything is based around schemas, and event dispatcher is also based around schemas. So we'll touch up on that later. So sales order details contains a sales order ID, which is order ID, and then some basically what sort of products have been ordered with that order. Okay, so enough. What I want to do is do some statistics on product level to see how many sales did we actually get for a specific product. And if I just write a query where I select from sales order detail and then join to product table by product ID, it's right there, then and order it by product ID, so we get all product ID. We'll see that there is one row for basically every single sale, total sales, for every single product. So in order this, so many sales have happened for this product 707, quite a lot of them. We can ask Mike Eason to pick up a calculator and sum all of them up and give us a result. But that would be quite boring for Mike. Why not? Jesus Christ. Still, in some instances, it will be quicker than our queries. That'd be right. 300,050 ish. Cool. I don't think that's right, but we'll check. So what we can do is we can ask SQL Server to go and sum it up. Anyway, as we clever guys, and we're learning shit. Yes, I did say shit. Anyway, so we're going to include the execution plan into this, so we can see what's actually happening. Right? So it's pretty simple. Last index on product on the product table, then merge to a sales order, and that's it. Give us some result. Do some sorting. Most of the work is actually involved in sorting things, because reading data is just streaming it off the page file, well, of the MDF file, and then joining it. It's also basically part of the stream that happens when you read the data. We're not doing any predicate search here, any predicate restriction here, so it's a pretty simple query. So that's why most of the work is actually spent sorting things. Alright, so what I want to do is to go and say to SQL Server, ask SQL Server very nicely, please, go and sum all of those numbers up, total sales, for every single product. So if I just put sum by this column, will it work?
No.
No, it's not. Why is it not going to work?
Because product ID needs to be either in group or aggregation.
Exactly. So, for example, if we do this, then we get column product ID is not valid and blah 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 because of group by clause. That's your indication. We need to include that in a group by clause because product ID is not part of the aggregation. How would I say it? Aggregation clause. So SQL Server doesn't know what to do with this. It needs to know by which fields we need to group and what other fields we need to aggregate for that grouping. That's where we say group by jam. Jam is our key, and then for every single product name or product ID in our case, we're going to go and find all the totals and sum all of them up. Oops. Okay. Product ID. Will it work now? Yes. Okay. So Nick was wrong about the number, obviously. Only by about 250 something. Anyway, okay. So that's how we can do like very simple grouping. Let's make it a little more interesting, and let's see how many. Okay, we've got the number of products we sold in total for every single product, but how many orders have been placed for this product in the first place? So how can we do that count? Just to count up all the orders. For example, each order can have multiple quantities of this product. For example, I can place an order for product 707. In one order, I can order 5. In another order, I can order 10. In the other order, I can order 1. So what we want to know is how many. Okay, this is how many sold altogether, but how many of those, how many orders of those products actually generated? What is it for? Is then we can do some calculation. What's the average order quantity per order? So when a customer calls in, how many items they actually order in one go? What we can expect. So any suggestions what we can do? Sorry? Somebody said. Okay, count. Yeah. So what are we doing? Okay. Orders will give our column and name. Orders, count, just count everything, right? So we look at the product ID as our grouping, and then for every single product ID, we'll go and find all the other rows. So that's going to be all our. In fact, let's just get through and go through it. Oh yes. So SQL Server is going through this result set, and it goes, okay, 707, this is what we group by, plus 1. Again, this is what we group by, it's previously the same one. Plus 2, plus 4, plus 1, plus 1, and so on. We can go on like this. This is how I can spend an hour doing this lesson. Plus 1, plus 2. Okay, and count, what it does is actually counts number of rows that we actually encountered. So this is how we can actually say that this there was one order for 707 of quantity of 2. We count them up, and we get, in this specific case, for example, these 2 orders would generate 3 products total ordered totally for 2 orders. So we get a count. Right. Then what we want to do is we want to get an average, or not average. What we want to do is we want to divide the number of sales for that have been placed all together by a number of orders that have been placed for those products, in order to get an idea of what's the average count. Well, what's the average order quantity per order? So we can do that by basically dividing this column, total sales, by a number of orders that's been placed. Right? Can we do that? Is it gonna work? No, it's not gonna work, because those things are actually result sets. So if we look at our execution plan again, I mean, we touched that on in a previous lesson. If we look at the execution plan, we're doing some selection. This is our basic restriction out of the sales order detail relation. Then we're doing some joins and so on, and then we actually generating, this is compute scalar. This is where we're generating the actual sum. Well, the stream aggregation, this is where we actually put everything together, and then compute scalar is where we actually generate the result. So because we can only include things that actually the results of our restrictions, results of our selects from tables in the actual select statements, we actually need to specify what we want, what values we want. We want a computed scalar value, let's put it this way, it's much easier to say, into our expression. Expression being like a function, basically, not a function like a mathematical function divided one by another. It's basically an expression. So, and this is going to be our average order quantity value, right? So, do you think SQL Server is going to be there because we're asking it to produce the same result twice effectively? Do you think it will be calculating this value twice? So, if we run this execution plan, do you think it will change? What do you think now?
It's another step for calculating
You're absolutely right. Yeah, it might. To be honest, I don't think it even will produce another compute scalar value, because that thing would actually produce 2 expressions. As you can see at the end of it, it's got 2 expressions. One of them is a stream from the aggregate. The other one, I think, is just doing the sum itself, or I think even the sum is happening here. So I don't think it will even will produce another compute scalar value, because SQL Server is smart enough to know we already done this work, so it assigns every single calculation effectively an expression output. Like here at the bottom in the output list, can you see it? It's got expression 1004. That's what we produced by basically I don't know whether it's a sum or a count that it was doing. I think it was just a sum, because count doesn't actually have any meaningful aggregation routine behind it. So to run this, then what we've done, we just basically divided this number by this number. The execution plan, ooh, it did change. Yes, well done. So although it did put another compute scalar, but it doesn't actually do the heavy calculation by redoing the sum again. Okay, right. So 6,266 divided by 3,083. Is it 2? I don't think it is. Yeah. Yeah, we didn't cast. Why do you think it produced 2?
Because the number of cells
Okay, and do you remember why it is the case? Yeah, and what's in the conversion table? Right. Do you remember, and I think it was one of the first lessons we had, there is a preceding conversion in SQL Server. So every single type can precede the other, and int is right at the top of them. So if there are 2 columns being divided, 2 values being divided, one is int, one is decimal, the result will be converted to int, and so on. And because we're actually doing conversion of int by int, so the result is integer. So we actually need to cast. We cast the whole value into, let's say, as float. Think it's going to make any difference? No. What we need to do is to cast every single result that we are dealing with into float. And then we get the right number. Okay, this is the proper route.
You should just do top up.
I don't know, let's give it a go. Yeah. What if we do the other way? Is it just any value or the first one that didn't count? Yeah, just any value. That basically that will indicate that float actually supersedes the int. Okay. Any other suggestions? I mean, this is what we're doing. We're producing a scalar value out of this. Any other suggestions how we can do the same kind of thing, but in a different way? How we can use the aggregation to achieve the same result? So this is effectively an average number of orders being placed. Exactly. Use average, not average function. So there's AVG, stands for average. Average of what? Order quantity. Exactly. We get 2. How can we now convert it? Can we do this to convert it into a proper number? We can. Okay. If you look at our execution plan, it has changed a little bit. Now the averaging is now happening sort of on the selection of the cells with a quantity there somewhere. Okay. So actually, if we let's just go back effectively to the amount of work that SQL Server needs to do when it's doing all the summing up and all that kind of stuff, you will find that this query for execution sake is actually much better than averaging, because we have to produce this result and this result anyway, so we might as well use the output of those values and do a very simple math to just go and divide them. Whereas averaging will actually happen in the aggregation routine itself, so it's right about there, and it will have to effectively do two things at the same time. Well, not 2 things at the same time. I don't think SQL Server is smart enough to figure out that we actually need those values anyway, so we don't need to do the actual average aggregation while we're going through every single row. Anyway, I think we spent enough time on this one. Right, okay, so coming back to this query, imagine we've done the average and it's all good. And do you think this number here is actually going to be a correct representation of number of orders placed? Okay, here's a question. What if what if the database design itself or architecture allows a customer to place an order for the same item in 2 lines, like our system, for example, does? We can just place the same item on the order in 2 different lines and specify different pricing information in there. Then, if we're doing this count effectively, then what we're going to see is they're going to be product 707, quantity of 1, 707 per quantity of another one, for example. So that they both belong to the same order. So in this case, we're going to get as if there were 2 orders for the same product, but in fact they were all placed in one. That's basically states that it's not. In this situation, it means that the database itself is not fully not in full proper third normalization form. Remember normalization forms? Okay. So if we have okay, crap, I didn't copy the table that I prepared here. But anyway, let's. I think it's quite an important point to sort of get across. So let's actually replicate this scenario. So let's create a table where we have some products. Imagine this is effectively our name, our order item table, quantity of products ordered, and then order ID that they belong to. Just let's work with table 1. It's easy to remember. Okay, we'll have jam, quantity of 1, order ID is 1, and then the pizza 1 for order number 2, and then jam again, quantity of 1 for order number 3, then jam again for order number 1 and order number 4. Okay. So select name from table 1 or by name, and then we sum by quantity and count all the rows. That's pretty much about right. Okay, so total number of jams sold is 3, and they've been placed in 3 orders. Let's mix it up a little bit. 2. Okay, 4 jams sold in 3 orders. It's a little bit more interesting. But then imagine, for example, we have. Let's alter that table so you can represent it even better. Okay, what I've done is I've added a unit cost in there as well. So we can say we sold this for £1 for 99p, and this one is for pound, this one is for pound, this one is for pound. Okay, and in our normalization, we haven't normalized the database fully, or for example, we actually allowed in our architecture for a customer to place an order where we have 2 lines for the same product, but we have different price for it. Maybe he had a discount for this product, so he got it for 99p, and this one he has to pay full price of 250. Okay, so if we run this query, what we now have is Jam sold 3 products for the same order ID. Run this for it, you can see we sold 5 jams, but now it says 4 orders have been placed for jam. But in fact, if we count all of them out, 1, 2, 3, 4. For jam, we only had 1 order, 2, 3, and that's it, only 3. So what we can do is we can actually in the count specify which column we want to count by. We want to count by an order ID column. That still produces the same result, 4. What we can say is, alright, how about Yes, we do distinct, right? Yeah, and it's like, wow, 3, cool. See what we've done? We actually made SQL Server to go and say, okay, only count up all the distinct values in order ID. Now, is it a good idea to do this? I mean, this is the result we want to get, and it seems to be a pretty valid SQL statement. So, we can easily do that to get the right number of orders. I mean, first of all, remember third normalization form? Okay, if we wanted to allow from the database architecture to allow the situation to happen in our database architecture, how would we have to change this table to allow for it? To bring it into full normalization form. Remember that there should be no duplicates. Okay, so we've got duplicates here. There's a duplicate right there. Effectively, even if we have jam as a product ID, and we're still effectively repeating the same line twice. So we should, because there's 2 different product pricing for it. So if we want to bring this table into fully normalized, third normalization form, we would have to move the unit cost out of this table. And ideally, we would want to move the order quantity out of this table and do an order quantity sum on every single product within the order. So we would, if I was very anal about the architecture of the database and I really wanted to bring it into third normalization form, that's exactly what I would do. I would actually create every single line has got the primary key, yeah, then it's got a foreign key to product table, then it's got the sum of all the items that have been ordered on for the specific product on this order. Then the order foreign key, of course, to know what order it actually belongs to. Then a foreign key to a pricing information for every single product, effectively. And within that, we have how many items, at which price they have been sold, with which discount, and so on. And within that, if we have different discounts for every single product, we would move it into another table, and so on, and so on, and so on. And then we don't have to do distinct on that. But obviously, if we overcomplicate the architecture to that point where we've got different pricing information for every single line, etc., it makes it very, very nice and academically correct way of doing the third normalization form, but it's going to be a bloody nightmare to select any data out of it. We're going to be doing too many selects, especially when our data grows. We'll have to do too many scans, too many merges, etc. It's much easier to keep it in the same table. And this is how we can go around this problem. We can only count up a distinct order IDs. Okay, so in here, run the execution plan. It looks cool, right? So, but we need to make a small change. We need to say, okay, I don't want to count up all the order. Here, we actually need to do order ID, I think. Sales order ID. This is the column that I need to count by, not just all the records. I also need to say that, you know what, I need this to be distinct. Distinct. And that distinct. And that's all cool and groovy. We get the result. Yeah, cool. Alright, so I'm pretty sure there's not going to be any duplicates there. Look at the execution plan. Jesus. It changed quite dramatically. Have you noticed? Let's compare them against each other. So this is our previous one without distincts. Okay, so nice and simple. Scan one table, merge to, well, join to another, do some aggregation, done. And here's with distinct, just by putting one little clause indication there in the aggregate, we end up with doing a lot more work. In fact, what we're doing is we're scanning. If we look at this, we're scanning the sales order detail table twice, just to produce a distinct. Okay, and because the scanning itself is actually takes most of the time, but you can see this aggregate here. This is what actually doing the. I think that might be doing the distinct bit. Or maybe this one is doing the distinct bit. We can't tell from the aggregation routine itself, I don't think. Provide product ID. Let's see if we can get this. Sales order ID. Oh, this one is doing distinct, this branch. of the execution plan. How do I know? If we look at the group by, we see, no, sorry, this one. If we look at the group by, we see sales order ID. So this is doing this distinct value, and this one we can't really tell what it's doing. All right, so obviously these functions here are very CPU hungry processes. Any kind of math that we have to do is a CPU hungry process. In fact, any kind of expression manipulation of the data that we have to do is a CPU hungry thing. Even if it's just, for example, one string plus another string. Pretty simple thing, just concatenating both, but it's still quite a heavy process. So we should really avoid them as much as we can on the SQL Server side of things. It kind of depends on the situation. For example, if you've got just one database server managing only one database on your server, and it's not as heavy as, we don't hit it like millions of times a day, then it's okay to do like this. Just let the SQL Server do all the math. Whereas in our situation, we've got multi-tenancy environment on the SQL servers, so lots of customers are querying the data, and in our case, we should treat this as a database really, instead of the actual computation engine to do all the sums. So my point being by doing this is just to demonstrate how much stress we can put in SQL Server, just putting things like this in our query. I mean, in effect, that's what we need to do, all right? So we need to get the unique number of orders. Basically, we need to count up all the orders, blah, blah, blah. So we stick distinct in it and don't think about it. But if we actually start looking at the execution plan, we start seeing that this is where our problems with our SQL Server slowdowns basically start occurring, because we don't think about how much stress we actually put on SQL Server with simple modifications like this. It's also worth knowing how SQL Server treats all those things that you actually ask it to do. Okay. I've done this, and this. Sorry? What I would suggest doing instead, if we need to, bring in a third normalization form, maybe, or not do it. Okay. Well, what we could do is think about, do we really need the unique order sales information? For example, maybe if we use this query all the time, then we need to maybe trigger it and put them in the static tables, all the sums, instead of doing the calculation on the fly all the time. Things like this are things to consider. Again, it's kind of whether you need it all the time. If this is the thing that gets run, all the time. Like for example, we have in the open order. For example, we calculate the number of in the inventory adjustment routines, when we calculate the number of products that are currently in open orders. What we used to do is just calculate them on the fly. But then every time we need that information, we have to actually do a lot of a lot of CPU hits on the server to calculate things like. Let's take all the orders, actually a couple of millions of them, go through all of them, select only the ones that are not processed, then go through them, every single one of them, row by row effectively, and sum them all up, and this is our order, on order quantity. Instead, we now calculating it through triggers and putting it, actually recording that information. Maybe it's the same kind of case here, where we kind of have to maybe on every single product line, or create a as well. We can create a statically populated table, or a static table that gets populated every time we raise a new order that increases the product count by 1. Another thing we can do is computed columns as well, but we'll talk about that later. Cool. Right, so let's move on. So we've done this one. That's exactly the same as the previous one. Okay, so next thing I want to do, so we have that query. It's all cool and groovy, and I think it still runs. Yes. changed it slightly, and now added product name and it as well, just for a second, so we can actually see it. But what I want to do is to add a product inventory count for every single line. So we've got 707. This is the product. We know it's sales, how many sold throughout the history. We know how many orders have been placed on it, and then what we also need to do in our query is to put the current stock level for this product in here. Okay. So pretty simple. Join to a product inventory table. Cool. And do the sum. Sufficient enough? Anyone?
Just got multiple inventory locations stuff, activating the same stuff.
Doesn't matter. I mean, if it's got multiple inventory locations, we still want to get the count because we want to get a count of all the stock levels that we have in all the locations for this product. Doesn't matter where they are.
Oh, no, I mean all this in sales in the same way. Yeah, well, roles will be duplicated if there are more sales orders, so you get more.
Yes. No. No. What we're selecting from? We're selecting from sales. What we're joining on to product. That's one-to-one relationship ratio. Because product to sales is product 1, many sales. Sales, then product inventory. Because we're selecting this specific order. Actually, yeah, we do gonna get duplication for sales orders. If there are 2 locations in that. That's a good point. Yes. What else? We're going to get the right inventory information if we're doing this join.
No.
Why not?
Well, we get just the inventory that was sold.
That's fine. That's what we want to know. There you go. Alright, do you think this 707 has got inventories level of 800,000 and 904? Not really. Why is that? Why do we get such a wild number in there? Yeah?
The whole stock level will be added up to
Yeah.
So the stock level will be multiplied by the amount of orders.
Exactly. So we can't do stupid stuff like this, you know, because what's actually happening? Let's go into this thing. Here's all the sales orders. No, actually, this is our inventory for product 707. It's 288 products. And here's all the sales for this product. Right there, we can see it's 3,083. Okay, so let's put them against each other. Do you remember what's happening when we're doing in a join? Nick, what is it in a join? We have 2 tables and we join them together. What do we get mathematically?
Contents involved only.
Yes, that's one thing, but in terms of mathematically, what do we get?
Product.
Exactly, we get a Cartesian product, which means we multiply all of this by all of this when we join things together. Right? Let's get our calculator. And we multiply 288, this is our quantity of inventory. We multiply them by 3,083. 3,083. And we get that wild number that we have at the top. Right? Same number?
Mm-hmm.
This is what we're getting. This is obviously it's wrong. We can't cheat it by saying, you know what? There you go. Hey! Valid point, isn't it? And then we don't have to do anything else. I mean, it's pretty cool. We can do it like this. But to be honest, if any other programmer saw this, like inventory level, what are you doing? You're taking this quantity and then you divide it by 7. What? You know, it doesn't make any sense. I mean, it does produce the right number, but as long as there are no repeats for sales orders IDs. But we assume that our database is in a third normalization form, which it never is, but assuming that it is. Okay, so obviously that's not right. Don't don't do that, Emma. Okay, so what we can do is we can actually calculate. I mean, we need to get that product inventory level out of it somehow. So any suggestion what we can actually do to get the right number? Subselect. Cool. Yes, you can do subselect. Instead of typing all that stuff in, I'm just actually going to paste that in. So what we're doing here is pretty much exactly the same thing, but here is we're actually going to calculate our sales statistics separately from our select itself. So we're doing all the aggregation as a separate view, effectively. So first of all, we're going to go and produce a almost like a view selection of all the order product IDs, how many of them have been sold and how many orders they've been basically sold with, etc. As I said, completely separate select. So we've got that information already aggregated. And we give it a name called sales. Then we're selecting all the products from product table, join them to product inventory table, and then join them to sales. This is our table, effectively. And we simply just output the sales total, sales orders out of this query, and we then summing up all the quantities. And we get the right information. And as Matt noticed before, because we've got in product inventory, we can have two stock levels for the same product in two different locations, right? So, do you think that query will give you the right result for sales and order quantity? For sales and total orders. Looking at the query, what do you think?
Still have multiple locations.
Hmm?
Still have multiple locations.
Yes. Sorry? If we have multiple if we have multiple locations in here, so we're going to have two lines for inventory in here. Are we going to get duplicate sales? No, they're not, because we're actually grouping them together here, and then we're doing the sum on the inventory level there. So this is the right kind of query that we need to do if we want to get that sort of information. If we look at the execution plan of it, it looks pretty neat, even just by looking at it, because it doesn't have like a Japanese underground network map on it. It looks fine, right? Just by first glance on it. And we can even test this query even further, whether the execution plan actually makes sense to the SQL server, because if we run this without any predicate, it still looks alright. But what if we said, well, actually I'm going to put the where clause in there. What we're going to say is, you know what? I want information only for a certain product. 707. I need to actually say which table we want it from. 707. There you go. Only for this product, I want to get this information. If you look at the execution plan, start analyzing it. It hasn't changed much. If we start analyzing it, and if we move all the way back to the scan, we can see in the predicate we limiting this the selection from the sales order straight away by 707. This is the bit that actually happens there, right? And it's because this predicate is included. Well, because this query is basically dependent on. It's only used with this query here as a subselect, effectively. We know that we don't need to select all the information, group it all together, and then use that as an output for the next query, even though that's what our SQL statement effectively states, right? We don't limit our selection to this subselect in any way. We don't have any predicates here. We simply just go dump everything. But because we included this predicate in our main query, SQL Server is smart enough to know that we don't need to select everything, so it includes this predicate in here, right, in the initial selection. You may just make sure that we've got aircon on. Everybody suffocates on there. Cool. So when you write SQL queries, I would suggest just run it with the predicate just to see how the execution plan changes. If you still see that this thing still runs individually and separately, then there's something wrong with the SQL query itself. Or if the query is way too complex, you can't understand the execution plan, well, if you can't understand the execution plan, your query is wrong. Or you don't know enough about the execution plans. But generally try to basically get the understanding, especially if you write a query that gets reused all the time, try to understand the query itself, put a predicate in it, in the actual final result. See whether that predicate actually gets propagated to all the queries that you use in all the subqueries. If it's not, your subquery is wrong. It needs to actually take that predicate into account. Right. What else do we have? Okay, right. So the final bit. Right. So what I want to do is to write a query that's a lot more complex than just a simple one SQL statement. Okay. So in TSQL, it's called transactional SQL because of many different reasons, but primarily, not primarily, basically what it normally refers to is that we can actually write a procedural code in SQL. So instead of just writing one command, we can actually write multiple, like we've done in today's example lesson, where we had something like this. Right, we got two results out. We can use both of those results in our client application. It will literally tell us, so we're going to execute 10 different things at the same time. Return 10 different result sets, and I'm going to iterate through every single one of them. That's fine, but we can also do things like this. We can declare a variable. One, that's going to be an integer. Declare another variable. 2, that's going to be float. We can set them some values. 1, set another variable, another value. 2, and then we can do something like select var 1 plus var 2. Okay, so we can write actual TSQL code, which is called a procedural code. Okay, and in some circumstances when we need to do a very complex selection, it's not a really good idea. It's sometimes necessary to break your queries down into multiple steps. So you're doing one operation, you then add into that result set, then you do another selection, maybe another subselect, you add in that. Basically, putting all this thing together. Like your final result, you assemble in from different bits. The reason for that, you can control the execution plan, you can control you can test the result of every single query, and so on. And you can also limit the amount of work that SQL Server is doing at every single stage. So, just give you a little example, or not a little example, it's actually a big example. Where is that example? Example, there you go. Let's start copying that through. First of all, I'm going to declare a parameter of our query. It's called product color. What sort of product? We're only interested in black color and black products. Okay. Then I'm going to declare a temp table. Temp table is basically a variable. We can declare a variable to be as if it's a table, and we can then declare what sort of columns it's going to have, like that, and then that becomes effectively a table. Okay. So we can select some data out of it, and we can insert some data into that table, we can delete data, we can update it, blah blah blah, and then once you finish the execution, this table gets gone. Hopefully, if the temp database gets truncated properly, which doesn't in our service. But yeah, that's the point of temp tables. So actually, in your SQL query, you can create a temp table, then put some stuff into it, and then get a selection out of this table. That's exactly what I'm going to do in my example. So first of all, I'm going to go and select, insert into this table, into my temp table, product ID, name, and list price information from a product data. So let's comment that out and just run it through individually so that to get the sort of result I'm actually going to be inserting a product selection table. This is it. It's just basically selecting everything from product, where color is black. This is where we specified it, and we're also selecting list price, blah blah blah, this kind of information. Okay, so we can now insert this into a product selection table, and we can then do some other stuff with it, for example. Okay. So we could do a sub-select out of this table now, and let's say where name, like, ll, and then wildcard. Like is wildcard operation, which means basically does exactly what it says. It's doing like instead of equal. Okay. So we now can do a sub-select on that temp table that we've created, and so on. So the reason why I want to use temp table in this specific circumstance is because what I want to do is I want to create quite a complex selection of all the products, get their name, get their current list price, then get their list price revisions, how many price revisions they had throughout the history of this product. What was the average list price for this product? What was the total sales and order quantity? Basically, I could, with a lot of thinking and a lot of, messing about, I can do all of this in one SQL with subqueries, but not with a lot of thinking. It's quite easy actually to do this, but imagine that this was a lot more complex than it is, given in this specific context. But I will have to do two subselects, then join them, then make sure that all the results are correct. So what I want to do is effectively break this selection down into manageable sort of pieces. And that's pretty much the point of actually creating temp tables and dumping some data into them, and then this kind of stuff effectively. So first of all, I added all the products I'm interested in. This is based on my predicate. And then what I want to do is update this information. As you can see, my number of list price revisions, the count of all the revisions that have been done for this product, and average list price are all nulls for this product. I want to update it, so I want to populate it now. So effectively, what I'm doing is I am doing a selection from a product list price history table, join it by product ID and grouping by product, and then counting all the revisions and doing the average list price on them. So that will give me all the product revisions for all the products that we have selected in the first place. And then I'm joining that to a product selection table and doing an update on those two columns. Everybody follows? If not, just basically shout, and then we'll go through it again, because I think I'm going to be too fast over this. But in case if you are not following this, say so, okay? Please. Anyway, let's see what sort of information we now get in the temp table. Now, basically, so we now have some the product that we have selected. We then updated that with number of revisions, price revisions that a product had, the average price, and so on. Now we need to do calculate the total sales and number of orders in place for this product. We're doing pretty much exactly the same thing there. So again, another update. So we're updating that product selection table with some more calculated values. And then we get those in place as well. And then we can finally get the result out to the client application, where we're doing some even further selection. So we're now also joining that product inventory table and doing the sum and so on, and now we get quite a complex query. We broke it down into 3. Reason for that, to look at the execution plan, executions are separate for every single select bit. We have a separate execution plan, so we effectively broke it down into specific chunks. The disadvantage of doing this is we actually created a product selection table. SQL Server doesn't do any magic. It will literally create that table on hard drive in temp DB database, where it actually does the operations. If it's got enough memory, it'll try to do it in memory. But once the table gets a bit too big, then it will be dumped on the hard drive, so you will have increasing I/O and so on. So not again, it's based on circumstances. There's no right and wrong here. Sometimes it's a good idea to do this. Also, it's a really good idea to control your execution. So, for example, we're doing a lot of stuff here. Wait for delay. 0, 0, 0, 0. Okay. What I want to do is I want to slow down SQL Server a little bit. I don't want all of this happening at the same time. Imagine we're doing very complex query, and we don't want to just basically dump it all on SQL Server and just now go and do it. Or we only go, okay, create a table and put some products in it, wait a little bit, get everyone else to finish what they're doing because we're doing something very heavy. Then put some more stuff in it and put some more stuff in it. And this is what's happening, okay? So our execution is a lot slower now. It's taking 3 seconds. And if that's not effective, we get the same data, but now at every single stage we slowed it down a little bit. We'll let everyone else to do some other things. While we put in something like wait for delay, so-called thread context switching happening on the SQL Server. So this is the same as we have in C#, for example, thread sleep. So we literally put this thread to sleep, so go like, screw you, go away for a second and just have a little rest. And while that wait for delay is there, some other users can actually execute something. So when we're doing some very complex sort of results, and obviously we can't do wait for delay, we can't control the execution of this query if we just put everything in one big query. Although the recommendation generally is not to do a procedural code in SQL Server. It's generally not a very good idea. From performance standpoint, it will yield a lot slower query that you would normally end up with if you just put everything in one big query. But it does give you a lot more agility and a lot more traceability, a lot more testing capability, and in some instances even better execution results, because we can split everything up. We could have a very difficult predicate that we know that SQL Server is not going to be able to figure out. Okay, cool. That's it. Any questions?